sequencing of reactor units and Levenshtein plots. So any questions about that problem? Yeah.
So if you had like multiple reactions, would you then change RA to be so RB if you wanted desired RB, or
If you were trying to design for the production of a single species, then you would want to put in the conversion that matches that.
okay, so you really would you just have to add the limits for your, I guess, limiting reagent.
Yeah, you could still do it in terms of the limiting reagent because that's where you're bounded by 0 to 1. The bounds would change if I were using B instead of A, if that ended up being my limiting reagent. But normally for multiple reactions, you wouldn't use a Levenshtein plot. And in those scenarios, you're usually trying to, well, one thing that you're trying to control for is selectivity as well. So just like when we stop, you might notice that we stopped putting everything in terms of conversion right when we started talking about multiple reactions. That's not a coincidence. So putting everything in terms of conversion of one species works great if you just got a single reaction that you're worried about. But keep in mind that a single reaction doesn't mean only one elementary step. It just means one set of reactants, one set of products. The first problem we did today, I wrote down 4 elementary steps. It's still a single reaction. N2O goes to NO2 and oxygen, right? All right, problem C, or problem 3. This one is worth how many points? 30. All right. This one's worth 40 points. What do you think there's left to ask you about? I definitely heard some people talk about pressure drop. This is a tough problem. I think it's tougher than it needs to be. Just be aware of that as we're going through it, that you won't get a problem quite this hard. Those last 2, I don't really think they were all that difficult, but this one's pretty damn tough. So just don't let this one freak you out too much. Okay, gas phase, catalyzed. A goes to B plus C. What type of reactor? Yeah, that's in the problem statement. It says it's carried out in a PBR system shown in figure 1. You know you're in trouble when the freaking thing has a figure. And what's labeled on this figure, I will put on the board. Okay, that's all that the figure has. All right, and the rest of the problem says pure A is fed into PBR1. At a rate of 0.4 moles per second and an inlet pressure of 3 bar. It says the entire system is at 700 Kelvin. And it says that the purification unit removes 50% of B that is produced in PBR1. Finally, the last thing that's given that the rate of consumption of A is equal to K times concentration of A over 1 plus little a concentration of B, and K is given as 0.20 decimeters cubed per kilogram seconds. A is equal to 100 decimeters cubed per mole. Any questions about the problem statement? Okay. Part A. Derive a differential equation that relates conversion to the weight of the catalyst in the second packed bed reactor and it goes on to say where x2 is defined with respect to inlet of the second PBR. So we just talked about that a little bit. How Fogler will sometimes define a conversion based on the inlet, and sometimes define it based on the overall inlet. Finally, it says, clearly define all parameters in your final equation. I'm not going to write that out. Assume delta P is negligible. So how do I get started?
Can you label X2?
Can I label X2? So what is X2? It's not going to help you for me to put a label up there right now. Yeah.
So why does the rate equation assume we're measuring CA in mass units and CP in mole units?
What is the mass in this rate equation? Catalyst. It's a packed bed reactor. The mass that you see in that rate equation is catalyst, not A, not of any species. These are concentrations, right? So this is the inverse of a concentration, but this is catalyst. Any other questions about the setup? Try to erase as little as possible. So what do I do?
Table.
Before that, let's ask a broader question. X2 says that it's to be defined based on the inlet around PBR2. Everybody see that in the problem statement? Does any of this matter? No, right? So don't let it throw you off. The X2 having that peculiar definition seems like a curveball. It's actually a life raft. That's how we're going to solve this problem much easier. We just have to worry about this is a PBR. Who cares that there's all this other stuff attached to it? He maybe could have asked it about PBR1, so you didn't have to recognize that, but anyway. Like I said, it's a tough problem. Okay, so what is the design equation? dx dw is equal to what? What's the prime mean? I don't know if you put it here, but we'll at least put it here now. What's the prime mean? Per mass, right? So PBR. divided by the flow rate, the inlet flow rate to what unit? So this is why there's that little thing in there about clearly define all your terms. The nomenclature is not given to you for pretty much any of these problems. He just uses natural language. He doesn't say P naught is equal to 3. He says the inlet pressure is 3. I think, yeah, 3 bar. So make sure that you know how to use the correct nomenclature and that you define your nomenclature. So yeah, FaO2 meaning O meaning the inlet, 2 meaning the second PBR. All right, that's design equation. What else do I write down?
Table.
Oh, we don't have to worry about pressure. Pressure drop is negligible. Rate law, that's the third thing we usually, no, you're right. I skipped over that in my eyes skipped over it because I'd already put it up here. So yeah, we'll write out the rate law that's given. And then what's the third thing that we want to do, right, is stoichiometry. It corresponds to the chapters in the book, right? This is chapter 1 and 2, this is chapter 3, and the derivation is in 9. And then this is chapter 4. Okay, so what concentrations do I need to worry about for my stoichiometry? A and B. A lot of times, homeworks or in class, we would just deal with A. But we have to do A and B because they're both in our rate. Right? The volumetric flow rate.